Well, hello there, ladies and gentlemen. So today we're going to continue on and look at another cycle. So we've looked at for the air standard cycle analysis, we looked at an arbitrary cycle, an example. We did some detailed numerical calculations. We looked at the Otto cycle, which is a spark ignition or a representation of a spark ignition cycle, primarily gasoline. So we got the Otto cycle, which mimics the gasoline engine as far as blackboard and thermodynamic work is concerned. So today we're going to look at the diesel cycle. Diesel cycle is a bit different than the Otto cycle because the method by which the fuel is burned and therefore the heat is added is a little bit different. So we're going to change one of the processes compared to the Otto cycle to achieve a diesel cycle. And then we're going to shift gears and look at an open system air standard cycle. So referred to as the Brayton cycle. So we're going to look at the Brayton cycle, which is an open system air standard cycle. This cycle mimics or is similar to a gas turbine, jet engine as well. So the Brayton cycle is used as an idealized, i.e. for blackboard thermodynamic work, an idealized either jet engine cycle or a gas turbine cycle. So we'll talk a little bit about the Brayton cycle today. We'll derive the efficiency of the Brayton cycle, get an expression for the Brayton cycle efficiency, basically W dot shaft divided by Q dot N. That'd be the definition of the efficiency for an open system. Open system here is going to be using shaft work as the output. And then we'll see if we can do a little example or at least get started on an example involving a Brayton cycle. Okay? Indeed, we'll relax some of our assumptions about internally reversible processes. We'll deviate a little bit away from the air standard assumption, and we'll assume that the compressor and turbine in the open system Brayton cycle are not 100% efficient, isentropic efficient. There'll be some irreversibilities in the cycle. So that'll be a little bit different today. Okay? So let's talk for a moment here about spark ignition versus compression ignition in internal combustion engines. So we have spark ignition. So we have spark ignition. This is gasoline. Gasoline engines use spark ignition to a spark to ignite the air-fuel mixture. So at top dead center, so here at top dead center, we have the piston here. So we have air and fuel. So we are at top dead center. So the piston is as far up as it's going to go on the compression stroke. Isentropic compression, if you like. And we have a little spark up here, a little spark plug. So here's our little spark plug up here. Spark plug. And a little spark occurs. So a little spark occurs and the air and fuel start to burn. Now the air and the fuel burn so quickly that we can model the reaction and therefore the heat addition as one of constant volume heat addition. So we have fast combustion from a spark. Spark basically nearly instantaneously burns the air-fuel mixture. So we have a fast combustion process. So we modeled it as isochoric heat addition. Okay, so that's what happened with the spark ignition or gasoline engine. Very fast combustion process, faster than the rate at which the actual engine is turning in terms of RPM. The combustion process is much faster than the speed of the engine, so we assumed it was constant volume combustion. For compression ignition engines, compression ignition, So this would be the diesel, for example. Diesel engine. The fuel is injected by a mechanical fuel pump. So here we are around top dead center. So instead of having an air-fuel mixture pre-mixed and ready to explode, we simply have air. We simply have air, not fuel, just air. And we have a fuel injector. So we have a little fuel injector here. So there's a little passageway here. And we are squirting fuel. Fuel injection. Okay, so we're squirting fuel into this highly compressed, high pressure, high temperature air near top dead center. And the fuel burns as it is injected. So fuel injected slowly. It's injected by a mechanical fuel pump. It's not injected all at once. It takes time. So fuel is injected slowly. Therefore, it burns slowly. Therefore, instead of assuming a constant volume, isochoric heat addition processes in the Otto cycle, we're going to assume a constant pressure heat addition process. Burns slowly, so we're going to assume that the heat addition process, i.e. the heat release during the combustion or the burning of the injected fuel, we're going to assume this is a isobaric heat addition process. Isobaric, constant pressure heat addition process. Everything else is the same as the Otto cycle. It's just we're changing the heat addition process. Just changing the heat addition process. So let's have a look here at the diesel cycle. Diesel cycle, air standard diesel cycle. So let's put up the TS and the PV diagram here. So here we have PV, and here we have TS. PV and TS. So process 1 to 2, adiabatic compression. Remember, the air standard cycle assumes reversible, internally reversible processes. No irreversibilities inside the piston cylinder device. No friction, no unrestrained expansion, no heat transfer inside the piston cylinder device across a finite temperature difference. So we're going to start off at state 1. So state 1 is the highest volume state, and we're going to adiabatically compress. Adiabatically compress the air. Remember, in the diesel cycle, we don't have an air-fuel mixture pre-mixed and ready to burn. We have air and we inject fuel when we want to start the heat release or the burning process. So for the Otto cycle, we start off with already mixed air-fuel mixture, and then we initiate a spark and the heat is released essentially all at once, very rapidly. So we approximate this as an isochoric heat addition process. But for the diesel, we start off with compressed, i.e. very hot, high pressure air, and then we inject fuel via a fuel pump with a fuel injector into the combustion chamber, into the hot air, and it starts to burn as soon as it hits that hot, highly compressed air. But it burns at a rate fairly slowly because we're limited by the rate in which the fuel can be injected by the fuel pump. And the fuel pump slowly injects fuel. So we assume that this is an isobaric heat addition process for the diesel, as opposed to an isochoric heat addition process for the gasoline or Otto cycle. Okay, so process 1 to 2 is adiabatic, internally reversible, therefore isentropic. So State 1 starts right here, and we have isentropic compression up to state 2. Temperature goes up because volume is going down. We're doing work, boundary work on the air, and it's starting to heat up. That's why temperature goes up from 1 to 2. Pressure goes up, volume goes down. Remember, we have a Vmax and a Vmin in the cycle, just like we did in the Otto cycle. But now, instead of having isochoric heat addition, we have isobaric expansion with heat addition. So we begin to expand. We begin to expand the air, and we add heat at the same time. So Qn occurs from state 2 to state 3. Okay, so we're adding heat isobarically. So that's a horizontal process on the PV diagram. Temperature goes up and entropy or specific entropy go up because we're adding heat. So now we have a temperature increase as we add heat and an entropy increase as we add heat. So delta S is positive from 2 to 3. From 2 to 3, okay? Then from 3 to 4, we have adiabatic expansion. We turn off the heat addition, and we allow the products of combustion or the hot air to expand out to state 4, and we allow it to occur adiabatically. If it's adiabatic and reversible, it's isentropic. So on the TS diagram, we have a movement vertically down, constant entropy down to state 4. And then we finish off the cycle back to state 1 with isochoric heat rejection, just like in the Otto cycle. So we have a constant volume, Q out, heat rejection, entropy decreases, temperature decreases, and we end up back at state 1. Okay? So the work-producing cycle here takes heat isobarically, converts some of it into work, boundary work in this case, and rejects the heat isochorically. PV diagram is quite informative because that tells you the various processes. TS diagram tells you where the heat addition is occurring. Okay, that's pretty nice too. All right. Now, I'm not going to go into much detail here. We're not going to derive the efficiency for the Otto cycle assuming constant specific heat, but I will write down the expression and talk about it. You can look, there is a separate section in the notes just on the derivation for efficiency for the diesel cycle. It requires a little bit more work because the process is a little bit more complicated. In particular, there is a second volume here. Remember, for the Otto cycle, the efficiency was a function of the compression ratio alone. So we still have the compression ratio here. We have R is equal to Vmax over Vmin. We still have the compression ratio. We still have the compression ratio. And for the Otto and the diesel cycle, the higher the compression ratio is, the more efficient the device is. But we have another volume here. We have this V3 volume. This is the volume at which the heat addition stops. So not only do we have Vmin and Vmax in the cycle, but we have this other volume that describes the heat addition process or how extensive the heat addition is. So we have this other volume here, V3. And for the diesel cycle, V3 is the cutoff volume. Is the cutoff volume. So that's the volume at which the heat ceases to be added during the isobaric heat addition process. So V3 is called the cutoff volume. And we have another ratio, RC, which is the cutoff ratio, and it's defined as the ratio V3 over Vmin. or if you like, V2. So this is called the cutoff ratio. So not only do we have the compression ratio, but we have the cutoff ratio as well that describes the diesel cycle. So in the expression for efficiency for the diesel cycle, you have a complicated relationship between the compression ratio and the cutoff ratio, which give you the efficiency of the diesel cycle. Let me write down the efficiency of the diesel cycle for you. I don't memorize this stuff, so let's see here. Eta for the diesel cycle is 1 minus, and it starts looking a little bit like the Otto cycle. So I have a 1 minus 1 over K, and then I have 1 over the compression ratio, R, to the K minus 1 power. Now that looks exactly, with the exception of the 1 over K, it looks exactly like the Otto cycle efficiency. The Otto cycle efficiency was 1 minus 1 over K minus 1. So we got this K in here, that's a little bit more complicated. And then we have in parentheses here, we have the cutoff ratio to the kth power minus 1 divided by the cutoff ratio minus 1. So we have this additional term here that makes the expression for the diesel cycle efficiency a bit more complicated. And it's because you've got this additional parameter dictating what the heat addition is. And we see that the efficiency has to do with the amount of heat being added. Okay? Now, one thing to note, as R sub C goes to 1, then this term goes away. So as R sub C goes to 1, in other words, V3 goes to V min. In other words, we don't add a lot of heat. So note as Qn goes to 0, R sub C goes to 1. And with the exception of this 1 over K right here, the efficiency of the diesel becomes similar to the Otto cycle. I will put similar to. We got this 1 over K in here, so it's not quite the same, but as R sub C goes to 1, this term goes to 1. Forget the 1 over K for a minute, but we have this compression ratio term. So the diesel cycle efficiency becomes similar to, not the same because we got this 1 over K, becomes similar to the Otto cycle efficiency. Similar to, that's what this tilde means. Now, why are diesels so popular in many applications? Well, they're very popular because they're often extremely efficient. Why is that true? Why are they extremely efficient? Well, for one thing, so advantage of diesel cycle. The primary advantage for the diesel cycle, pretty much the only advantage, I guess, is you can have much higher compression ratios. So R for diesels, much higher, often much higher than Otto cycle. Remember I was saying for Otto cycles, R for Otto cycles, the compression ratio, usually around 10 to 12, usually around 10 to 12. That's the compression ratio for Otto cycle engines with spark ignition, okay? And as I discussed last time, we can't really get a lot higher than that because if you pre-mix the air and the fuel together and you increase the compression ratio too high, you'll get uncontrolled combustion that causes knocking. Anything higher than around 12, direct injection is helping with that a little bit, but anything higher than 10 to 12 and you start getting knocking, okay? You can use higher octane fuel. Higher octane fuel is more resistant to knocking, but highest compression ratios for Otto cycle are around 10 to 12. On the other hand, for diesels, where you're compressing air, not air fuel, you don't have this inherent problem with knocking. The rate of heat release is controlled by the injection rate for the fuel, and we have pretty good control over that. So knocking is not really a problem, a technical problem for diesel development, so we can crank up the compression ratio quite high. And notice here that as the compression ratio gets very high, this entire term gets very small, and the efficiency of the diesel cycle goes to the efficiency of 1. Very high efficiencies are possible with a diesel because we can crank up the compression ratio. For most diesels, R for diesels usually range anywhere from around 16 all the way up to 22. Very high compression ratios. You got yourself an old indirect injection diesel, like from a Mercedes from the 80s or the 70s, you're looking at a compression ratio of about 21.5 to 1 or 21.5. Very high compression ratios are possible with diesels. Therefore, efficiency of the diesel is usually greater than the efficiency of the Otto cycle because you can get such a high compression ratio, okay? You can't get too high or you start having mechanical problems. You'll end up getting very high friction. You have very high compression ratios and pressures. You have to make the engines very bulky, heavy to withstand the forces associated with those high compression ratios and high pressures. Okay, so the primary advantage of the diesel is we can have higher compression ratios and therefore higher thermal efficiencies for the diesel cycle. A good diesel cycle will probably get around 30 to 40% thermal efficiency. A good Otto cycle will probably get around 20 to 30, maybe 30. Those numbers are going up with recent technological advances and the use of direct injection in gasoline engines as well. Gasoline engines are typically now going towards the diesel cycle, even though they use gasoline. And they're able to do that because they can inject. They're developing high pressure pumps and high pressure systems for injecting gasoline. So gasoline engines are actually going more towards the diesel cycle with the use of high pressure direct injection for gasoline engines now as well, okay? Okay, I think that's enough about the diesel cycle. You can read the section on the diesel cycle, and in the homework, you'll probably have a diesel cycle to analyze. Once you do one cycle analysis, you've done them all. We've already done one detailed cycle analysis problem. That was in the early part of the chapter a few days ago. So once you've done one cycle, you pretty much have done them all. Just the processes are a little bit different, okay? All right, let's take a break for a second here, and we'll move on to Brayton cycles.